Hey, ladies and gentlemen of CSM 3040, it's Todd Usher here, and we're going to do a brief review of psychrometrics in practice. We're going to go through one quick exercise and show you how we can use the psychrometric chart to calculate some differences in two different air streams. So first, I want to just review the chart that we've talked about previously in class. If you remember, we have dry bulb temperature on the bottom x-axis, and when we move left to right in temperature, we call this sensible temperature. That's just the temperature that we read on a thermostat or a thermometer. As we increase in temperature, we're adding heat. As we decrease in temperature, we're removing heat. Then also remember, going up and down on the psychrometric chart is where we're changing the humidity in the air, otherwise known as latent energy in the air. All right, so let's get to our quick exercise. This is real world. So if you're a mechanical engineer and you're trying to calculate how much air and how much energy it's going to take to heat some outside air that you're bringing into a building to condition the building, this is exactly what we would go through. So in this particular scenario, we're given that the outside air temperature, the dry bulb temperature, is 10 degrees Fahrenheit. Pretty cold, probably not Clemson, South Carolina, but 10 degrees Fahrenheit and 50% relative humidity. And we're going to need to heat that air up to 115 degrees to bring it into our building and heat the space. And then it further tells us that we need 1,000 cubic feet per minute of supply air at 115 degrees coming into the building. So we need to figure out how much enthalpy or energy, enthalpy is just a fancy word for energy, how much energy we're going to need to put into that air to heat it up, and then how much air we're going to need to bring into the building from outside. So again, this is a pretty simple situation that as a mechanical engineer we would have to calculate when we were sizing a system for our building. All right, so the first thing we're going to do is we need to find on our psychrometric chart and plot the outside air and then our supply air. Okay, so we're going to plot our outside air, 10 degrees, 50% relative humidity. And we're not changing humidity. We're just adding heat to this air. So the only thing we're affecting is the dry bulb temperature. And it comes straight across horizontal line to 115 degrees. Okay. So now we want to find the enthalpy in our outside air and our supply air. And the difference between the enthalpy in these two different masses of air is going to be the amount of energy that we're adding to the air, to a pound of air, to heat it up to 115 degrees. So pretty straightforward. The enthalpy scale is on the outside of both axes, and all you have to do is take a ruler or straight edge and line up the enthalpy scales on both sides so that they go through the same numbers and match up while they go through the point that we've plotted for our airstream. Okay, and so with this we find that the difference between our outside air and our supply air is 25.2 BTUs per pound. So we've added 25.2 BTUs to every pound of air that we've brought inside and heated up from 10 degrees to 115 degrees. Okay, pretty straightforward. The next thing we need to do is determine the specific volume of our supply air. All right, we've been told we need 1,000 cubic feet per minute of supply air, but we need to figure out how many pounds of air that's going to be. So we can see that our supply air at 115 degrees is going right through the 14.5 cubic feet per pound specific volume line here on the psychrometric chart. All right, now to figure out how much air in pounds per minute we need to be bringing in or supplying to our space, all we have to do is multiply 1,000 cubic feet per minute and divide it by 14.5 cubic feet in every pound of air. We cancel our units and we get 68.97 pounds per minute of air that we're going to supply to the space. So we've basically taken this measure of cubic feet per minute and converted it to pounds per minute simply using our specific volume of air. Okay, so now that's not quite enough because all of our equipment is rated in the mass flow rate per hour. Remember, we're typically talking about BTUs per hour or tons of heating and cooling. So we're going to need to convert these pounds from pounds per minute to pounds per hour. And that's just a simple multiplication. We take 68.97 pounds per minute, multiply it by 60 minutes in an hour, and boom, we get 4,138 pounds per hour. And that's the amount of supply air at 115 degrees that we need to supply to our space. So 4,138 pounds per hour. So now we know our pounds per hour. Now we can calculate our BTUs per hour. Because remember, our equipment works on BTUs per hour. It's rated on BTUs per hour. So we're simply going to take our pounds per hour that we just calculated, multiply it by the enthalpy or energy that we're adding to this air to heat it up, and we get 104,276 BTUs per hour. Pretty big amount, pretty large amount of heat we're having to add to that air, but it makes sense. We're bringing pretty cold air in and we're heating it up. So the next thing we need to do is find how many cubic feet per minute of outside air we're going to have to bring in that we're then going to heat up and supply to our space. We know we need to supply 115 degree air at 1,000 cubic feet per minute, but we need to figure out how much air we're going to bring in from outside, right? So what did we learn in class? We talked about what happens when we heat up air. The volume that 1 pound of that air occupies increases, right? As the air temperature gets hotter, the air volume is going to expand and increase. So what we need to do here is simply plot our specific volume of our outside air and our supply air and just do a little ratio. So we've got supply air at 14.5 cubic feet per pound, outside air at 11.9. We do a quick ratio by dividing our outside air volume per pound by our supply air volume per pound, and then multiply it by 1,000 CFM. And boom, there you go. You've got 817 cubic feet per minute of outside air that we need to bring in to be equivalent to 1,000 CFM of supply air. And this makes sense, right? Because we know that as we heat the air up from 10 degrees dry bulb temperature to 115 degrees dry bulb, it's going to expand. So we can kind of check our math here, and we can see that, yeah, 817 cubic feet per minute coming in from outside. We're going to heat it up, it's going to expand, and it's going to be equal to 1,000 cubic feet per minute of supply air. So let's just review real quick. We had 69 pounds of air flowing through our system per minute at 115 degrees Fahrenheit. That's equal to 1,000 cubic feet per minute. At 10 degrees Fahrenheit, that's equal to 817 cubic feet per minute. The difference between these two is expansion and contraction of the air based on dry bulb temperature. Okay? Pretty simple. Hope that makes sense. We'll do some practice next.